Good afternoon, everyone. My name is Andrey Fedotov, and today I'd like to present a lecture that we developed jointly with Alexey Vishnyakov. I will be talking about the CASR, or CASR, an open source tool which stands for Crashes Analysis Severity Report. And crashes could be an outcome of fuzzing, and this project is going to be useful for both developers and security experts. Well, much has been said about fuzzing during the morning session, and all I can add is that a successful fuzzing results in new challenges that you might face, such as a number of crashes that you will have to analyze, and oftentimes it's done by both developers and security experts alike. So they face a number of problems in this regard. The very first one is quite clear-cut. You have too many crashes, and if you fuzz lots of different projects, not only would you have lots of crashes, you will have lots and lots of crashes. And if you try to automate the analysis and crash analysis and duplication avoidance removal, you'll see that depending on the approach used, you will get different outcomes that you will be happy or unhappy with. Therefore, you need a systemic approach to this. Oftentimes, crashes are analyzed with the help of debugging, that results in overheads and additional cost. For instance, fuzzing in CI is usually done in Docker containers or somewhere in the clouds, and that means that it's not always convenient to launch, start, or download the container to your machine. It takes time. And what you want to get initially is a summary of the crash. And after analyzing this data, you make a final decision whether you're going to debug it further or not. In addition to that, there are a number of various programming languages that the software is based on. Therefore, the definition of a crash is different. For instance, for binary code, it's an exception. If we're talking about Linux, for instance, actually it's a signal, not an exception. However, if we are talking about in secure languages or interpretable languages, we're talking about exceptions. Therefore, the very definition of a crash is different for different languages, and you need to analyze it if you want to support several languages. In addition to that, there are different types of fuzzers, and this is a result of having different programming languages. If you want to automatically analyze the fuzzing outcomes, you have to be prepared for different presentation of results. For instance, IFL or a fuzzer outputs are different, so they require different approaches to analysis. And the last bullet, by the way, is as follows. Even if you successfully dedupe the data, you will still have a pool of crashes that you would like to prioritize to better understand what to start with. And in my presentation, I'll try to give you the answers to the issues I just stated. This is the outline of my presentation. First, I will give you a brief overview of the existing crash triaging tools. Then I will move on to the CASR project and outline its main features. Then I will move on to the fuzzing crash triage pipeline, following which I will move on to analyzing not just crashes but also undefined behavior sanitizers. It's also useful because you will be able to detect different types of errors with that feature. Then I'll tell you how to integrate that into the VM system. And in addition to that, I will also tell you how to export crash reports to serif format, which will help you analyze them in the IDF. And I will brief you on the libCASR library that allows you to develop your own tools for crash analysis and triage. Right, let's move on to an overview of the existing crash triaging tools. There is a GDB plugin. It's been around for a decade. It's no longer been supported or further developed, but everything started with this particular plugin, which is called GDB Exploitable. You launch the GDB and it analyzes it analyzes the crash, and actually it analyzes the criticality of the error to identify whether it's a crash or not. If you look into the issues in GitHub, you'll see that oftentimes people describing errors would accompany it with a screenshot of this tool. Another existing tool is the IFL triage. If you'll take a closer look at the AFL++ tool list, you'll see a number of tools recommended by the authors, and I liked the AFL triage most of all out of the entire list because it dedupes the stack traces, and I believe that that's the best compromise, so to speak, because it allows you to get good results. However, one of the cons of the IFL triage is the lack of filtration. If you dedupe the stack traces, then it makes sense to filter out irrelevant functions. The aforementioned tools are no longer supported. That's another con. Upward is another tool. It has nothing to do with fuzzing. It is used in Ubuntu for crash reporting. However,
есть как бы вот это понятие самого отчета.
It acquires data, sends it to the developers, and they can just read it without launching anything to draw some conclusions, which is useful. Cluster fuzz was mentioned time and again during the day. It's the OSS fuzz backend. It also features dedup, which is based on heuristics, and it compares the Levenstein distance between stack traces. One of the pros of the cluster fuzz is that it does have the filtration function. We used as a basis their functions and files, so we kept all the licenses, and then we started adding our own filtration functions in our tool. As for the motivation, we started using fuzzing, and one of the problems that were faced boiled down to the fact that it was easier for us to add a fuzzing target than analyze crashes from the previous runs. We decided to do something about it. The fuzzing process, the starting points, will be covered by the follow-up speakers. I will not deep dive on that, so I will just focus on the crash analysis. Some history. The CASR project was not initially about analyzing crashes. It was a hobby project aimed at analyzing the core dumps, and we would get reports on the core dump analysis.
Собственно, core dump, которые являются следствием одних и тех же ошибок.
Most of them were caused by the same errors, so we decided to develop another tool called CASR cluster for dedupe purposes. Simultaneously, we developed fuzzing, and as soon as we started getting too many crashes at the fuzzing stage, we realized that we needed to do something, and we already had some backlog, so we just started using GDB instead of core dump, and following that we developed various tools for automation purposes. The common things are now part of a library, and this is the way the tool looks like right now. Since we started everything with the core dump analysis, I will briefly go over this tool. It is based on the idea of ideas from exploitable and apport that I touched upon previously. So the idea was to get a report with useful information on what happened during the crash. We try to extend the standard apport report by adding network connections, open files. We thought that it would help us pinpoint the root cause of a crash, and we also added the criticality analysis. I hope you can see the screenshot on the slide. This is the way the CASR crash report looks like. You can analyze the data, and well, one of the useful things is that we see the launch line followed by criticality evaluation. Here it says buffer overflow, right? So we'll take this into account. It is followed by stack trace. It's a torch vision pre-parsing library, and below you see part of the open source code. And one thing that I'd like to draw attention to, it's not the first element of the stack trace that you can see on the slide. It's number 2. So irrelevant frames, which are part of sanitizers, are filtered out, and we only leave those elements that are part of the user side code. As you can see, the crash was caused by memcmp function, which is a read function, which means that either we have a problem with indices or the buffer allocated. We analyzed the report, and we didn't have to launch anything. We have initial data on the causes of the crash, which is useful. Sometimes you can just take a look at the report and understand how to fix the crash, or you can just understand that it's a false positive, or then you realize that you need to launch a GDB for a follow-up analysis. So I told you about the crash report, and the next important element is the crash severity estimation. It's not about running a complicated analysis. Rather, the goal is to highlight something which is already clear for the user to immediately understand that it makes sense to analyze it firsthand. For instance, we all know that program counter rewrite or using any values is a critical crash. So it is worth analyzing, because otherwise it might cause critical vulnerabilities. As for the third bullet, for instance, not exploitable things will not cause security breaches, so it's not a top priority. As far as exceptions are concerned, in Rust and Go, C++, Python, and Java, there are some useful messages that contain semantics on the crashes, so we can extract that data and include it in the report. Let's move on to the fuzzing crash triage pipeline. We have a number of tools such as CASR scan, CASR GDB, CASR Python, and CASR Java, and they generate these reports for different sources. Then we can dedupe these reports. I will brief you on that later on. The deduplicated reports can be loaded into the DFM system of DefectDojo.
То вы будете добавлять DefectDojo только те крыши, которые новые.
You would only feed new crashes into the DefectDojo that you identified during the specific iteration of the fuzzing. In addition to dedupe, you can declusterize the reports that would reduce the crash's scope even further. In addition to that, you can use a console utility tool in addition to DefectDojo, and there is another tool
Я бы тут сказал, что это довольно уникальный инструмент, потому что
that works with UPSAN errors. I haven't come across such tools in open source yet. It's shown to the side because UPSAN crashes should be analyzed in a different way because they are not crashes per se. Let's move on to the create crash reports tools. CASR SAN runs program with crash and seed, and then it parses the outputs of sanitizers. So it extracts stack traces. It also extracts panic messages if they are available. It also gets termination signals from an app. And for instance, IFL++ gets
аборт, он вызывается, да?
stack trace from GDB when it's missing in output. The sanitizer report will not be generated in that case, so we use a different tool which is called CASR GDB for getting GDB reports. In other words, you will get some useful data in any case. To get the code line that caused the crash, we need to introduce filtration to extract the code line and get the crash line. In addition to that, it estimates severity according to the error type. For instance, if you believe that
аварийные завершения при записи, они более критичны, чем при чтении. Вот такой подход.
memory writes are considered exploitables. CASR GDB is another tool. We also use here a small size library to launch GDB in the patch mode, and it also extracts useful data such as stack traces, registers, and that helps you estimate the severity. In addition to that, it extracts panic and exception messages, it parses the crash line, and reads crash source code. As you can see, these two tools use different sources, but their functions are quite similar. Which means that we might want to create a library. This is something that we noticed, and we started using it in the API. CASR Python and CASR Java tools operate in a very similar way. They extract exception messages either natively or from FRS and CASR, and they also extract crash lines, source code lines. If the crash is in the native side, then you launch CASR SAN that works with sanitizers and gets reports for the native parts. Let's move on to dedupe. CASR cluster loads all CASR reports. It filters out noise from the stack traces for dedupe purposes. It also removes recursive function calls, and then it compares the stack tracers. If they're identical, then the crashes are considered to be identical. Stack traces, well, if all the elements are equal, then the stack tracers are identical. If you have a code line and a file, you compare them if they're present in both elements. If they are not present, then you move on to the module. And the offset in the binary module. Otherwise, you rely on linear addresses, and we turn off the randomization for report generation, which gives you some sort of stability, especially if you will have to analyze the addresses unless you have other information. And this is the way to remove duplicate crashes. In addition to deduplication, you can also run clustering. In our case, we used the Microsoft Rebucket algorithm. The paper is quite old, but we like the technique. And this algorithm was used by Microsoft. When you get a message, do you want to send the error to Microsoft? You send it to Microsoft, and they cluster this error with the help of this technique. I'm not gonna go into details. All I want to mention is that first you need to run pairwise comparison of stack traces based on metrics, and the results will be from 0 to 1. Then you do a hierarchical clustering, and as an outcome you get a number of clusters. Moving on, I told you about the tools that are used for generating reports and clustering. Now we can go a level up and try to automate the fuzzing results triaging. There are AFL and libFuzzer-based categories. They are used for parallel CASR reports creation, deduplication, and clustering. They also copy crushing input seeds next to CASR reports, because as soon as you analyze the reports and if you decide to launch something, you'll try to look for input, and it's right next to you, which is quite convenient. In addition to that, they are used for printing cluster summary. It's cumulative statistics on the crashes, which might be useful, and sometimes analysis starts with just that. In addition to sanitizer reports, you can also get additional GDB reports, which is useful for comparison's sake. This is an example of an output of the CASR libFuzzer tool. As you can see, we had 362 crashes after the dedup. It's 44, and ultimately it was clustered into 23 clusters. You get statistics for each cluster. For instance, this is the cluster type, its criticality, the crash line from the code, and if you don't want to read the entire report, you can just open up the crash lines in the editor. Let's talk about the opson. We added this feature just recently, and as soon as we were done with the common crashes, we decided to focus on opson errors. Opson by default is not a crash, and this is quite logical, and this is something that you should deal with. There are lots of errors like that, and you get lots of them at the startup of your app before you start processing input data. And such errors might be valid. So if it's not a crash, you need to analyze both the crashes and the input corpus. That's the first difference. The second difference is that when you launch an OOPSON program, you get several errors rather than just one crash, and you need to take this into account during your analysis. We decided to remove deduplication for errors, and we decided to analyze the crash line in the code. This is a screenshot of the CASR OOPSON. Well, you might not find enough useful information here, but the main idea is as follows. Even after dedupe of the crash line, there are still lots of errors. For instance, here we're talking about 200 plus errors. However, for each error, you can generate a report for a detailed analysis. If you don't want to do that, there is a code line showing you the root cause and the error type. We are running a conservative analysis, but otherwise later on you will be able to add white blacklists for hash functions. If it's valid, you don't need to do that. That's the CASR OOPSON report example. We see a message, and it's quite informative because we see that one figure is added to another figure. There is an open source code line showing the location of the error, and the UTMP variable is summed up with another variable, while the UTMP line is received from the input data, which is the line above. And that allows you to prepare some fix. My personal impression is that the OOPSON errors are more about local stuff, not similar to crash. Therefore, deduping stack traces is not necessary. And there are too many errors, and we want to reduce them as much as possible. Now let's move on to vulnerability management. It's the next step after analyzing the crash analysis in one fuzzing sessions. But there could be several fuzzing sessions in CI, and of course you want to manage these results. Therefore, we modify the CASR-Dojo reports in the following way. After the dedupe of reports of one fuzzing session, you can upload them into the DefectDojo. They're all uploaded to your machine. Then you run deduplication, and you will only receive back new reports that were not previously stored on your VM machine. This is a screenshot of the DefectDojo. This is the way automatic report uploading looks like. This is a project tag, fuzzing goal tag, crash tag, so you can click on them and deep dive. This is a classical report that I have already demonstrated to you, but this is now within the VM machine. If you scroll down, you'll see not just the open source code, but also the stack trace. And in addition to it, you will get input data in your VM machine. It will also upload the CASR report there and the GDB report if it's available. Just recently, we also added the serif support because we decided that it would be a useful feature. The way it works is as follows. You have, after a fuzzing session, you get a list of CASR reports. You can upload them into a single serif report and then download VDE, and then you will use IDE rather than CASR viewer, and you click on a crash, and it contains some useful information on the initiation line, the crash type, and you also get a stack trace that you can click on to get additional data, which is useful and convenient. And if you lack a small part of the code, which is in the CASR report, you can download it into the Serif and then get data on the open source code lines. Now, if I may, I'd like to say a few words about libCASR. libCASR serves as a basis for all the analysis tools, and it gives you an interface for parsing the stack traces. It's one of the core technologies for dedup analysis. It allows you to generate all the reports listed here, as well as triage, crash reports, in other words, deduplication and clustering of both reports and stack traces. It depends on what you want to get. It also provides you severity estimation. It supports various sources and languages, and for severity estimation purposes, it also supports several architectures. If you are interested in developing your own tools, then you can use Rusty to code your own analysis tool. It's an example of a code in the libAFL, and most of you know what that is. It's a framework for fuzzing, which is gaining steam, and it demonstrates good results in the fuzz bench. This is the main part of the code for integration, which is stored in libAFL. I think it would make more sense if I told you how it works. libAFL is just a toolbox for phasing. In the fuzzer, you get an observer which is tasked with analyzing crashes. So you built in a function that analyzes crashes on the sanitizer side. This line of code is provided by sanitizer. You get a stack trace in the form of a line vector. Then you convert it into a structure, you filter it out, and you get a hash or a number. And then we feed to the observer the hash, and if it's a unique hash, then the crash is stored. If the hash is not unique, then the crash is not going to be stored. So in theory, the dedup can be built into the dedup function can be built into the fuzzer. And this is an AFL example. The hyperlink will give you more details. I recently double-checked it, and it seems to work. And now I'd like to demonstrate to you a brief fragment of the combination of the two tools. We're going to analyze crashes for PyTorch. First, we launched the phaser, clip phaser to detect crashes. Then we used AFL++ for fuzzing, and now we need to analyze all the crashes detected. So this is the CASR libFuzzer storing, and it generates a CASR report. Then we will download them into the VM machine. As you can see, it says 117, 30 clusters. it's one of the reports, a large PyTorch stack trace. Something is happening here. This is the code line, the crash line. The begin line was probably incorrect, and it probably caused the crash in the first place. Now we will download the outcomes into the DefectDojo, or actually it has already been done. Now hold on a second. We're launching the DefectDojo now. Actually, we launch CASR AFL, but that's the state memory limit, but it's a normal situation because you're limiting the memory use, and some of the crashes are stored in a separate folder. So 800 crashes were reduced down to 200, and now there are 50 clusters. Then you can analyze them cluster by cluster. This is the way the report looks like, similar to all the previous ones, and it's clear why the crash happened in the first place, because of an empty vector, and you don't get it back. So what happens next is you have two outcomes for two fuzzing sessions, and you download them into the VM machine. First, you need to create a volume or a config for downloading the reports, because you cannot do everything automatically. For instance, you need to manually specify the project name. And it reads here that 30 reports have been downloaded. So the first 30 reports have been downloaded. Then you start uploading the second project, and 4 of them were not downloaded because they were found in the previous fuzzing session, and then it uploads 200 remaining reports. This is the DefectDojo, the PyTorch. These are the fuzzing outcomes, and it's a typical CASR report in your VM machine. GDB report, severity estimation, and this is the code line that I already demonstrated to you. You can scroll down and analyze the entire crash information. SEED, the CASR report, and GDB report are the 3 files that you get. As for steps to reproduce, well, it actually shows you how to reproduce the crash. And that brings me to the end of my presentation. I told you about the CASR project, the way it is structured, its functionality, and I told you that it can be integrated with various fuzzers, with the VM system, and we use it in-house. As far as I know, some of the Russian community participants already started using it. The project was welcomed by the international community as well. Many guys from the AFL++ community use it. So if you are engaged in fuzzing and crashes analysis, use the CASR. Contributions are always appreciated, and well, like it on GitHub, the developers will be happy. Thank you so much for your attention. Hi, thank you so much for your presentation. I have a couple of questions. First and foremost, as far as I understand, your product is compatible with AFL or Unicorn AFL, right? And have you had any experience in using it in fuzzing without open source products? Well, we did not try to fuzz anything with Unicorn, but as far as user mode QM, if we don't have open source code, then we will use CASR GDB for report generating. And well, as for emulation, we have not used it so far, but in theory, you could probably generate such reports. And my second question is, Is it compatible with your other product, which is fuzzer, or it uses a different triage mode? Well, it's compatible because you can go through libFuzzer or AFL++. So in our case, it's AFL based. Therefore, CASR and AFL are compatible. Thank you.
Все, всем спасибо.